our series on numerical methods in civil engineering, we are going to continue our discussion on solving nonlinear equations. Last time we looked at the Newton-Raphson and secant methods for solving one-dimensional nonlinear equations. This time we want to generalize the concept and talk about some general iteration methods for solving nonlinear equations. We are going to first talk about equations with one variables, one-dimensional nonlinear equations, and then we are going to extend our approach to multi-dimensional nonlinear problems. So, both Newton-Raphson and secant methods can be regarded as special instances of a general theory of nonlinear equation solving, and for instance, nonlinear iterative method of equation solving. For instance, when we are interested in finding the value of x by doing a series of iterations. So, we are interested in finding the value of x at step n plus 1, provided we know the values of x at the previous steps. Now, for instance, the most general method, iterative method, xn plus 1 is a function of the values of x at m points. So, it is not only the function of the value of x at n minus 1 or n, it is actually a function of the values of the function at m points. So, it is a value of x at n minus 1 up to n minus m. So, this is an mth order iterative method. So, in that case xn plus 1 is a function of x, the value of x at the nth iterate, at the n minus 1th iterate, and so on up to n minus mth iterate, right, and that is why it is called an mth, it has got m points, right. So, that means that xn plus 1 is a function of the value of x, of the value of the function at value of the function as well as its derivative at those m points. When m is equal to 1, we recover the one point iteration method. Basically, the Newton-Raphson method is a one point iteration method. The secant method is a 2 point iteration method, because it looks at the function values at n as well as n minus 1, right. To find the value at n plus 1, we look at the values at n as well as n minus 1. So, the secant method is a 2 point iteration method, while the Newton-Raphson method is a 1 point iteration method, but we can have in general iteration methods with m points. Suppose that for a 1 point iteration scheme, we have a sequence xn plus 1 is equal to phi of xn generated with a certain initial value x0, and let us suppose that this sequence is convergent. So, as we increase the number of iterations, as n goes to infinity, xn goes to our known solution, which is our unknown solution, which is alpha. So, we can say alpha is the limit of xn as n goes to infinity, and since the sequence xn is convergent, we can as well say that it is the limit where xn plus 1, it is the limit of xn plus 1 as n goes to infinity. Since the sequence is convergent, it does not matter whether we take xn plus 1 and xn, because both of them are going to tend to alpha. But since once we write it as limit xn plus 1 in the limit n goes to infinity, we can write it as limit of phi of xn as n goes to infinity, since our iterative scheme says that xn plus 1 is equal to phi of xn. And since phi of x is continuous, we know that as n goes to infinity, x of n goes to alpha, we know that, right. But since this function phi of x, phi is continuous, so as xn goes to alpha, phi of xn will also go to phi of alpha, which is not necessarily true if the function phi is not continuous. But since the function phi is continuous, we know that as xn goes to alpha, phi of xn is going to phi of alpha. Hence, the limiting value of the sequence xn is a root of the equation phi of x is equal to x. So, when xn reaches alpha, right, then we have phi of alpha is equal to alpha, right. We have alpha is equal to phi of alpha. So, what does that mean? That means the limiting value of this sequence xn is a root of the equation phi of x is equal to x, right, because in that case alpha satisfies this equation phi of x equal to x exactly. So, alpha is a root of this equation. Thus, if we define, if we have a given function f x, and from that function we define f of x is equal to phi x minus x. So, finding the root of f of x, finding f of x is equal to 0 is equivalent to finding the root of phi x equal to x, right. So, it is clear that if we find the root of, since we have found the root of phi x equal to x with a sequence x n tending to alpha, we have also found a root of f of x is equal to 0, right. So, we are converting this equation f of x equal to 0 to finding the root of f of x equal to 0 to finding the root of this equation phi of x is equal to x. Alternatively, we can therefore state, to solve the equation f of x equal to 0, we can try rewriting it in the form x is equal to phi of x, and then which defines an iteration method automatically. So, once we write this, we automatically get an iteration method like this, and the root of, and once this iteration method converges, that is going to be a root of f of x is equal to 0. Next, let us look at conditions for convergence. But when will this sequence phi of x is equal to x, or x n plus 1 is equal to phi x n, when is that sequence going to converge? What are the sufficient conditions for that sequence to converge? Suppose that x is equal to phi of x has a root alpha. So, let us suppose it has a root alpha, and let us suppose that the derivative phi prime of x exists, and it satisfies the condition mod of phi prime of x is less than m, which is less than 1. So, that means the derivative is bounded, the derivative of phi of x is less than some number m, which is less than 1 in a certain interval in a neighborhood of my solution. So, in a certain interval neighboring my solution alpha, let us suppose that the derivative phi prime x exists, and also the derivative phi prime x is bounded, that is, its value is less than some specified value. In our case, we are saying that specified value m is less than 1. So, let us suppose those conditions hold. So, phi prime x is less than 1 in the interval j, where j is such that any x belonging to j is its distance from alpha is less than some value rho. So, if I take take alpha as the center, since we are draw a circle with radius rho, all my x's, we are considering all the x's which are going to lie within that circle, and we are saying that for all the x's which lie within that circle, the derivative phi prime of x is bounded and is less than some constant m, which is less than 1. Then in that case, if we start with some value x0 within that interval, so we are starting with some value x0 within that circle with center alpha and radius rho, then if we start with that value and then put that in our iterative scheme, that is, put that value here, right, in phi x0, get x1, then substitute again x1 here, get x2, and so on and so forth. If we continue our iteration scheme starting with a value in that interval, then we are guaranteed that all our new iterates are going to lie within that interval. So, what it says is that for all x0 belonging to j, xn also is going to belong to j for all n0, 1, 2, right. So, all x1, x2, x3 and so on and so forth, they are all going to lie within that circle with center at alpha and radius rho. And secondly, and the limit, as I increase the number of iterations, xn is going to go to alpha, right. So, it is a very beautiful concept. It says that basically I start with when I am sufficiently close to the root, convergence basically means that if I start with any value which is within a certain neighborhood of the root and the derivative exists within in that neighborhood and the derivative is bounded, then I am bound to get convergence, because my limit, my sequence xn in the limit n goes to infinity is going to tend to alpha, number 1, number 2, number 3, alpha is going to be the only root in J of x is equal to phi of x. So, if I satisfy these conditions, then these are going to follow. How can we prove that? Well, let us suppose we start with a point within J, and let us see if we can prove that if we start with a point within J, then if all those conditions are satisfied, then any new iterate is going to lie within J. How can we do that? From the definition of the sequence and the fact that the sequence is convergent, that is phi of alpha is equal to alpha, we can write xn minus alpha is equal to phi of xn minus 1 minus phi of alpha. Why? Because xn is equal to phi of xn minus 1 according to my iterative scheme, and since it is alpha is the root, so alpha is equal to phi of alpha, right. So, I can write this like this, and then I use my mean value theorem. If I use my mean value theorem, I can write xn minus alpha is equal to phi of xn minus 1 minus phi of alpha is equal to phi prime, the derivative evaluated at a point xi n, such that xi n lies between xn minus 1 times alpha times xn minus 1 minus alpha, right. It is just the mean value theorem. This difference is approximated by the derivative evaluated at an intermediate point times the interval size, which is xn minus 1 minus alpha. This is going to be true such if there is a xi n which belongs to J, right, belongs to this interval, right. Xi n is going to belong to J because xi n belongs to xn minus 1 and alpha, and I already assumed that xn minus 1 belongs to J. So, since xi n lies in that interval, it obviously means that xi n also belongs to J, right. And then if I take mod of both sides, I have xn minus 1, xn minus alpha is lesser than or equal to m times mod of xn minus alpha. Why? Why is that m? Because I know that anywhere in that interval J, right, my derivative is bounded, right, my derivative is going to be less than m, right. That was our assumption, that phi prime exists and phi mod of phi prime is less than or equal to m less than 1. So, that means that this phi prime xi n has to be less than m. So, we have m here, and since we have taken mod of both sides, we have mod of xn minus 1 minus alpha, and since xn minus 1 belongs to J, this thing must be less than rho, right. So, mod of xn minus alpha is less than m rho. What does that mean? That means that xn also lies within J, right, because xn minus alpha is less than m rho, and what is my J? J is such that x minus alpha is less than or equal to rho, and since xn minus alpha is less than or equal to m times rho, some fraction, right, m is less than 1, right. So, since this is less than this obviously means that mod of xn minus alpha must be less than m rho. So, xn must be lying within that circle which I drew with center alpha and radius rho. Thus, by induction, if x0 belongs to J, x1 is going to be, so we started with any arbitrary xn minus 1 which belong to J. So, if I start with x0, I know that x1 is going to belong to J, since x1, and then if x1 belongs to J, same argument, x2 is going to belong to J, and so on and so forth. So, all my iterates are going to lie within that circle, right. So, that is the first requirement of convergence. So, when I am within a sufficiently close neighborhood of my root, and then if I satisfy those conditions on the derivative, then in that case all my iterates will be lying within that circle. So, repeated use of this expression gives me xn minus alpha is lesser than or equal to, this I already got, right, xn minus alpha is lesser than or equal to m times mod of xn minus alpha. Then if I use the same procedure on this, I can show that mod of xn minus 1 alpha is going to be less than m times mod of xn minus 2 alpha, and so on and so forth. So, eventually I can show that this is going to be less than mn m to the power n times mod of x 0 minus alpha, and remember x 0 minus alpha is within that circle with center alpha and radius rho. So, that means that as I keep on iterating, I am going to get x n minus alpha is going to be less than m to the power n, and remember m is less than 1, right. So, m to the power n is going to become smaller and smaller as n increases. So, eventually my x n is going to converge, right. So, since m is less than 1, so this shows that whatever would be the starting value x 0, as n goes to infinity, x n minus alpha is going to 0. Thus, we have proved the second part, which was that this is going to converge, right, that this sequence limit x n is going to converge as n goes to infinity. And finally, to prove C, we said that in that case alpha is going to be the only root in that interval, in that neighborhood J, right. So, let's see what happens in case there is another root. Is that possible? To prove C, we suppose that x is equal to phi x has another root b within that interval J, such that b is not equal to alpha. That means the b also satisfies the phi of b equal to b. It satisfies that equation, sorry, not b, phi of beta equal to beta, but beta is not equal to alpha, right. Then, using the convergence of the sequence phi of x and the mean value theorem, we get alpha minus beta is equal to phi of alpha minus phi of beta, because both alpha and beta are roots of this, right. Phi alpha minus beta, then I again use my mean value theorem. So, this I can write as phi prime of xi times alpha minus beta, so long as xi belongs to alpha beta, which means that xi belongs to J, since both alpha and beta belong to J. So, this lies in that interval, function is continuous, so xi must belong to J. So, thus if then again we take the mod of both sides, mod of alpha minus beta is lesser than or equal to mod of phi prime of z, which is m, which has to be less than m, which is the condition we said, times mod of alpha minus beta, which is less than mod of alpha minus beta. So, m, since m is less than 1, this has to be less than mod of alpha minus beta, which is not possible, right. Alpha minus beta cannot be less than alpha minus beta, which is impossible. This is a contradiction. Thus, our original assumption that phi of x has another root beta in that interval is false, and hence alpha is the only root of J, only root in J of x is equal to phi of x. The iteration method x n plus 1 is equal to phi of x n is in general a first order method, unless phi of x is chosen in some special way. What do I mean by a first order method? That means that the order of convergence is normally first order, unless there are some special conditions on phi of x. We know that Newton-Raphson is a second order method, right, while the secant method we found was not really a first order method. It had a convergence value, it had order somewhere between 1 and 2, something like 1.6 something, right. So, in case we choose, so in case we have to improve the order of convergence of that method, in that case the function phi of x must satisfy certain additional properties, right. What are those additional properties, and how do those additional properties influence the order of convergence of the function? So, that is what we want to talk about next. So, let us assume that phi of x is p times differentiable in a neighborhood of alpha. So, if I take p derivatives, for p derivatives, all those derivatives exist, right. So, p derivatives exist in a neighborhood of alpha, where alpha is equal to phi of alpha, alpha is a root of that equation. So, let us also assume that all the derivatives of phi of x up to order p minus 1 are 0 at alpha. So, this is the crucial part, this is the additional assumption that we have to make. We are making the assumption that all the derivatives of phi up to the order p minus 1 are 0 at the root alpha, right, and the derivative of order p is not equal to 0. So, if under those conditions we can show that the order of convergence can be higher, right, and how high will it be? Well, let us take a look. So, in that case, since all the derivatives up to order p minus 1 are 0, if we use Taylor's series expansion for x n plus 1 equal to phi of x n, this is from our iteration algorithm, right, x n plus 1 is equal to phi of x n. I can write this as phi of alpha plus x n minus alpha, and then I do a Taylor series expansion about alpha. So, if I do a Taylor series expansion about alpha, what do I get? I get phi of alpha plus, in the normal course of events, I would have first derivative phi prime evaluated at alpha times x n minus alpha plus the second term would be phi double prime evaluated at alpha times x n minus alpha square by factorial of 2, and so on and so forth, right. But remember, what is our condition? Our condition is that all derivatives up to order p minus 1 are 0 at alpha. So, all the p minus 1 derivatives, they vanish, right, because that they are all 0 by our assumption, and then we are left with only the pth derivative, and we can evaluate the pth derivative. If we treat this as a remainder term in the Taylor series, we can cut off our Taylor series at that point. If we can write this as phi pth derivative of phi evaluated at xi n divided by factorial of p times x n minus alpha to the power p, where xi n belongs to this interval, right, where xi n belongs to this interval. But phi of alpha is equal to alpha, since alpha is a root of this equation phi x equal to x. So, this and this, so this I can replace by alpha, right. So, I get x n plus 1 minus alpha. By bringing phi of alpha to the left hand side, I have x n minus 1 alpha, and this is phi to the power p xi n by factorial p times x n minus alpha to the power p. So, what does this remind you? So, here on the left hand side we have x n plus 1 minus alpha, which is nothing but the error at the n plus 1th iteration, because this is epsilon n plus 1. It gives me how much, if I take the mod of this, it gives me by how much the n plus 1th iterate differs from the root, right, and that is my error at the n plus 1th iteration. While on the right hand side I have this term. What is this term? It is the error at the nth iterate, x n minus alpha is equal to epsilon n. So, now I have a relation which says that the error, the mod of the error at the n plus 1th iteration is less than this term multiplied by the mod of the error at the nth iteration to the power p, right. So, this is, recall, this is, we emphasize this when we are talking about the Newton's method and the secant method, that if you have to establish the order of convergence, you have to be able to write the n plus 1th error in terms of the nth error, right. So, we have just done that, and in the limit as x n goes to alpha, we have epsilon n plus 1 to the power divided by epsilon n plus 1 mod to the power p phi p alpha, because now x n is going to alpha. So, xi has to tend to alpha too, right, because everything is converging to alpha. So, we have this thing which is a constant and which is not equal to 0. Why is that not equal to 0? Because of our requirement right here, which says that phi prime of alpha is not equal to 0, right. So, this term is a constant, this is not equal to 0, and we have our error at epsilon n plus 1 is equal to this constant times p times the error of epsilon n. So, just by looking at this, we can say, let us think of Newton-Raphson. Let us think of Newton-Raphson. Newton-Raphson, we know that p is equal to 2, that is the order of convergence is equal to 2. So, what does that mean? What does that require? So, in terms of this requirement. So, for Newton-Raphson to be quadratically convergent, number 1, the function must have first derivative which is equal to 0 at alpha, right, and the second derivative p is equal to second. So, the first derivative must be 0 at alpha and the second derivative must not be 0 at alpha, right. So, that is the requirement under which Newton-Raphson is going to give me second order convergence, right. Thus, the iteration method xn plus 1 is equal to phi of xn is of order p for the root alpha if phi of j alpha, that is the jth derivative of alpha for j is equal to 1 to p minus 1 is equal to 0 at alpha, and the pth derivative phi p alpha is not equal to 0 at alpha. Let us recall that for Newton-Raphson we can write xn plus 1 is equal to xn minus f of xn by f prime of xn. So, in that case what is our phi? Our phi is nothing but this function on the left hand side, right. So, we can write phi of xn is equal to xn minus f of xn by f prime of xn. Hence, phi of x is nothing but this, and phi prime of x, if I take the derivative of this is equal to this, right. And let us recall again what is our definition of a simple root of f of x. Alpha is a simple root of f of x, then f of alpha is equal to 0 and f prime of alpha is not equal to 0, right. Since f prime of alpha is not equal to 0 and f of alpha is equal to 0, what can we say about phi prime of alpha? Phi prime of alpha is equal to 0. Why? Phi prime of alpha is equal to f of alpha. F of alpha by definition is 0 because alpha is a root of that, and f prime of alpha is not equal to 0. So, this is never going to blow up, right. This is going to be bounded, right. This is going to be bounded, but on the top we have 0. So, that means that phi prime of alpha must be equal to 0, right, and if phi prime of alpha is equal to 0 and phi double prime of alpha is not equal to 0, then we are going to have quadratic convergence of Newton-Raphson. Thus, we are guaranteed that the Newton-Raphson is at least quadratically convergent for simple roots. If in addition f double prime alpha is equal to 0, then we can show that phi double prime alpha is equal to 0. In that case, the Newton-Raphson convergence is going to be at least of third order, right, because the second derivative is 0, third derivative may or may not be 0. If it is not 0, then it has to be at least third order. If it is 0, then we are going to have even higher order convergence, right. So, in that case, if phi double prime alpha is equal to 0, then the Newton-Raphson method is also going to be convergent at least up to third order. There are many general methods for constructing. So, we can see that we can make the Newton-Raphson scheme, we can make the in case this condition is satisfied, Newton-Raphson is going to be third order convergent, but that is in case that is satisfied. But by construction, the Newton-Raphson method is second order convergent, right, because we saw that whatever be the function f of x, so long as this condition is satisfied, which is our prerequisite, right, f prime of alpha is not equal to 0, right, in that case the Newton-Raphson method is going to be second order convergent, right. But in case in addition if we have f double prime equal to 0, in that case we can have higher order convergence of the Newton-Raphson method. There are many general methods for constructing iteration schemes with higher order of convergence. It can be shown that for a one point iterative scheme of order p requires computation of p quantities. Basically, we need to compute p quantities. What are those quantities? The function and its first p minus 1 derivatives. Therefore, as you can see, to improve the order of convergence, there is a cost, right, because each time you need to calculate a derivative, it is expensive, right. So, if you can improve the order of convergence, you can have as many higher order of convergence as you like, but ultimately it is no longer economical, computationally economical, because the cost of taking all those derivatives, right, you can say you can lower the order of convergence. So, by lowering the order of convergence, what are you going to get? You are going to converge in fewer number of iterations, right. We are going to converge in fewer number of iterations, but the cost of taking all those derivatives and converging in a fewer number of iterations is going to be more than the cost of calculating less derivatives, where the order of convergence is less, but the number of iterations is more, right. So, if you take a lower order method, you need more iterations, but you need to compute only a limited number of derivatives. So, it all depends on a trade-off. So, it turns out that if you have to compute more and more derivatives, then the cost of reducing the number of iterations is is offset by the cost of calculating the derivatives. So, people would prefer to take a comparatively lower order method, do more number of iterations, and that is computationally more efficient. So, the convergence properties of an iterative method tells us how the error behaves as n goes to infinity in the limit of the sequence. However, in all our derivations so far, we have assumed that there is 0 round off error, right. So, when we calculate phi of xn plus 1 from phi of when we calculate xn plus 1 from phi of xn, we are assuming that there is no round off error. But in reality, there is going to be obviously going to be round off error, because whenever we compute phi of xn, we are not going to compute phi of xn exactly, we are only going to compute it up to our machine accuracy, right, because we are using finite precision arithmetic. Our computer has that many limited floating point numbers it can store for my mantissa, right. So, I am bound to get some round off errors. And how are those round off errors going to affect my convergence? So, that also is interesting. Hence, round off errors are inevitable. Hence, it is useful to find an estimate of the error after a finite number of iterations, an estimate that takes into account the effect of the round off, right. So, up till now our convergence laws, convergence relationships, they have all assumed that round off is non-existent. So, let us denote by x1, x1 bar, x2 bar, xn bar the sequence of approximation. Why are we using a bar on top? Because we want to denote them as the real sequence of approximations, meaning they have round off in them, right. While x1, x2, x3, xn did not have any round off, they are sort of our ideal iterate values, which assume that there was no round off. Let us now consider x1 bar, x2 bar, xn bar, where there is round off, right, and let the error at each stage due to round off be denoted by delta I, right. Then we can write x bar n plus 1 is equal to phi of x bar n plus some delta n, right, because there is this round off, right. So, delta n is my round off for n is equal to 0, 1 and so on and so forth. So, this is going to be true at every stage in our iteration. So, subtracting the converged sequence alpha is equal to phi of alpha from both sides. So, we subtract alpha equal to phi of alpha from both sides. So, we have x bar n plus 1 minus alpha is equal to phi of x bar n minus alpha plus delta n. Again, I use my mean value theorem. So, phi of x bar n minus alpha, I am going to write it as, because alpha is equal to phi of alpha, right. So, phi of x bar n minus phi of alpha, I am going to write as phi prime of xi n times x bar n minus alpha, where xi n belongs to x bar n and alpha. I can only do that because alpha is equal to phi of alpha, right. I can use my mean value theorem here. Then, if I subtract phi prime xi of n x bar n plus 1 from both sides and rearrange terms, I am going to get something like this, which is basically 1 minus phi prime xi n times x bar n plus 1 minus alpha is equal to phi prime xi n times x bar n minus x bar n plus 1 plus delta n. So, let us assume bounds on both the derivative and the error. So, let us assume that the derivative is bounded, right, that phi prime xi n is lesser than or equal to m less than 1, which is what we assumed earlier, right, remember. So, that is what we assumed earlier, and let us assume that a round off error is also bounded, which is true, right, because round off error is bounded by the, we have seen that in great detail earlier in the beginning of the course. Round off error is bounded by things like machine precision and things like that, right. So, the round off error is also bounded, and let us suppose that bound is delta. We therefore get, by taking mod of both sides, mod of x bar n plus 1 minus alpha, and then if we take mod of this, what is this going to be? This is going to be 1 minus m, right, because mod of phi prime xi n is less than or equal to m minus 1. Then if I divide both sides by 1 minus m, this has also got bound m. So, phi m times mod of x bar n plus 1 minus x bar n divided by 1 minus m plus delta by 1 minus m, right. So, this gives me a bound on my x bar n plus 1 minus alpha. This gives a bound on my error at the n plus 1th iteration that takes into account the effect of round off, because of this term, right. So, this says that at any stage in my iteration, at stage n plus 1 for instance, my error is going to be bounded by these values, right, and these are two parts you can see. So, the first part is what is known as the truncation error. In any numerical method, in any this we talked about also right at the first class, in any numerical method there are bound to be two types of errors. Any numerical algorithm for solving a problem, there are going to be two types of errors. One type of error is going to be the truncation error, the second type of error is going to be the round off error. Why do we have the truncation error? The truncation error is because we are approximating an infinite sequence by a finite number of terms. In this case, we are approximating alpha, which is actually the limit of the sequence phi of x n. It is the limit when n goes to infinity by the term after the n plus 1th iteration. So, we are approximating the infinite term on the sequence by the n plus 1th term, right. So, because of that there is an error, and that error is my truncation error, and this error is my round off error. So, the above is a strict bound on the error using known quantities. The first term represents the truncation error due to the use of the n plus 1th term in the sequence to estimate the infinite term, which is my converged value alpha. So, that is my truncation error. The second term represents the round off error due to use of finite precision arithmetic. Any prime computer, I do not have infinite precision, finite precision arithmetic, that is going to give me that error. The second term is a bound on the round off error. This is very important though. The second term is a bound on the round off error in the last iteration, since it is a bound on delta n. Look at this, delta is a bound on mod of delta n, right. Delta is not a bound on delta n minus 1 or whatever, right, any time in that. It is a bound on the error in the round off error in the last iteration, right, which is very, very crucial. Let us see why. It is important to note that the second term says nothing about the round off errors during the previous iterations. It deals with the round off error in the nth iteration. This means that the round off error in the solution is going to depend on the round off error only in the last iteration, which is very, very important, because what does that mean? That means my round off errors in the previous iterations are not contributing to my final round off error. Why? Because those round off errors are cancelling each other out, which is very otherwise you can see that if they do not cancel each other out, then my error is going to be significantly larger. So, the round off error in the solution depends only on the round off error in my last iteration, right. since it means that the round of errors in the previous iterations are self correcting, that is, they cancel each other out, right. It also means that it is not necessary to compute with full accuracy in the first. This is a very, very important result, because in lots and lots of places it is used all in multi dimensions. This has got very important implications, right. So, it is not necessary to compute with full accuracy in the first few iterations. So, we will see, I do not know if I have talked about this here, but if I am going to talk about it later on. It has got very important implications. For sufficiently large number of iterations n, the round of error is the dominant contribution to x bar n plus 1 minus alpha. You can see that, because as the number of iterations goes up, the truncation error is going to become smaller and smaller, right, because my solution, my n plus 1, as n increases, my x bar n plus 1 becomes a better and better approximation to my root alpha, right. So, as I increase the number of iterations, the truncation error is going to become smaller and smaller, as actually as I go to alpha, the truncation error is going to go to 0, right. But my round of error is not going to go to 0, right. My round of error is also always going to be there, right. So, increase in the number of round of error is the dominant contribution to x bar n plus 1 minus alpha. So, increase in the number of iterations then do not lead to any significant change in the truncation error, because as I go, as I am reaching the limit of the sequence, the contribution of the truncation error is becoming negligibly small, right. But my round of error remains at a constant magnitude of delta 1 minus m, where delta is a bound on the round of error in the last iteration, right. Next, let us recall that the convergence estimates we got for the Newton-Raphson and secant method hold true only for simple roots. For multiple roots, the Newton-Raphson method, for example, is only linearly convergent. So, we will talk about improving the convergence of Newton-Raphson for multiple roots, but at this point I want to talk a little bit about this error bound a little bit more, right. So, basically we saw that because this error bound depends only on the error in the last iteration, on the round of error in the last iteration. So, it is not important to calculate for the first beginning iterations to be calculated with great accuracy, right, because their accuracy is not going to determine the round of error. The round of error is going to be. So, this has lots of implications, because for instance, when you have multiple, when we are solving a nonlinear problem in multiple dimensions, and we want to use a Newton-Raphson update formula, right. Newton-Raphson update formula, as you can see in we will see that in more detail later, but the main cost of the update is the cost of calculating the derivatives, right. Okay, so, if you have a multidimensional function, the derivative, the Jacobian, is no longer going to be a single term, it is going to be a n by n term, right. So, the Jacobian, forming that Jacobian, and if necessary inverting it, so those are extremely expensive operations, right. So, what does that mean? That means, so the accuracy is not that important in the first iterations, first few iterations. Accuracy only becomes important towards the end, right. That means that towards the beginning, it is also not necessary for me to calculate all those derivatives to a great deal of accuracy, right. It is not necessary for me to calculate all those derivatives to a great deal of accuracy, and because of that, there are things like modified Newton, quasi-Newton, and things like that. We try to approximate those derivatives, right. So, try to approximate those derivatives so that they are easier, cheaper to calculate, right, to reduce the cost, right, because we know that what we do in the beginning of our iteration is not going to be that crucial, right, unless I do something absolutely weird that is not going to be, which makes my solution diverge, that's not going to be that crucial, right. So, that is why this is very important. Now, let's look at multiple roots. We recall that the convergence estimates we got for the Newton-Raphson and secant methods hold true only for simple roots. For multiple roots, the Newton-Raphson method, for example, is only linearly convergent. So, is it possible to improve the convergence properties at multiple roots? Well, let us take a look at that. So, recall that a root alpha of f of x is equal to 0 is said to have a multiplicity q if we can write there exists a function g of x which is equal to x minus alpha to the power minus q times f of x, where q is the multiplicity of the root alpha, and g of alpha is bounded, right, that is mod of g of alpha is less than infinity, is greater than 0. So, what this basically means, that there exists a function g of x which can be written as, if I take out the q roots of alpha, right, which I take my original function of f of x, I divide it by x minus alpha to the power q, I take out the q roots of f of x, the function which remains, let me call that g of x, and that function g of x exists, right. What does it mean exists? That means that g of alpha is not 0 and is not infinite, is bounded, right, and it is not 0. So, that means there exists a function g of x which I can write like that in case f of x has root of multiplicity q, right. However, so we saw that for the Newton-Raphson method, if it has multiple roots, if it has 2 roots for instance, if it has 2 roots, then we are going to get linear convergence. However, by slight modification of the iteration algorithm, it is possible to recover quadratic convergence. What is that slight modification? Well, originally we had xn plus 1 is equal to xn. For the Newton-Raphson method, we had xn plus 1 is equal to xn minus f of xn by f prime of xn. So, now I am saying that instead of having xn plus 1 equal to xn minus f of xn by f prime of xn, I am going to have xn plus 1 is equal to xn plus q times f of xn by f prime of xn, where q is the number of is the multiplicity of the root alpha, right. So, that is well fine and good, but that assumes that I know a priori beforehand how many roots there are, right. It assumes that I know beforehand what is the value of q, how many roots there are, right. But suppose we do not know that, then what can we do? Alternatively, convergence can be improved by adopting the following algorithm, which supposes that f of x is q times differentiable in a neighborhood of root alpha of multiplicity q. So, let us suppose that the function is differentiable at least q times, right, q being the multiplicity, right, it assumes that q is f is differentiable. In that case, since f of x is equal to g of x minus alpha to the power q, since alpha is a root of multiplicity q, so I can write f prime of x is equal to g prime of x minus alpha to the power q plus g of x times q times x minus alpha q minus 1, just taking the derivative, right. So, f prime of alpha is equal to 0. Why? Substitute alpha here, both sides go, these two terms go to 0. So, f prime of alpha is equal to 0. Similarly, f to the power j alpha is going to be equal to 0 for any j less than q. You can see that, because if you take derivatives up to less than q, there is always going to be a term x minus alpha, right, in these in the right hand side, and when x becomes equal to alpha, that term is going to go to 0. So, f j alpha is going to be 0 for all j less than q. Then we can write f of x, again doing a Taylor series expansion of f of x about alpha, right. Then f of x can be written like this, because again f of alpha is going to be 0, f prime of alpha is the second term in the Taylor series, f prime of alpha is going to be 0, f double prime of alpha is going to be 0 up to order j, where j is less than q. So, all those terms in the Taylor series are going to go to 0, and the only term, and the term which is going, which is the first term which is not going to go to 0 must have derivative of order q, right, because for all j less than q, f j of alpha is equal to 0. So, in the Taylor series we are going to evaluate this derivative at alpha, because we are expanding this Taylor series about alpha, right. So, all those j terms, j less than q, are going to go to 0. So, the first term that is going to be survive is going to be this term, and if we treat this term as the remainder term, we can write it as x minus alpha to the power q times qth derivative of f evaluated at xi, where xi belongs to the interval x alpha, divided by factorial of q, right. So, that becomes my f of x. And what is my f prime of x? F prime of x, I just take the derivative of both sides, x minus alpha q minus 1 f q of xi q minus 1 factorial, where xi belongs to alpha. So, now what do we have? Let us write u of x is equal to f of x by f prime of x. Then if we write u of x by divide by x minus alpha, and then if I take the limit as x goes to alpha, what is u of x? U of x is f of x by f prime of x. So, f of x is this, f prime of x is this. So, if I divide this by this and I divide that by x minus alpha, I am going to get 1 by q. I am going to get 1 by q. So, what does that mean? What does that mean? That means that the equation u of x has a simple root at x is equal to alpha. Why? Because if I take u of x and divide it by x minus alpha, then in the limit as x goes to alpha, I am getting a constant, right. If this were not a simple root, then there would have been terms like, there would have been other terms like x to the power minus alpha on this side, right. I have got u of x, I am dividing it by x minus alpha. If u of x had more than one root at alpha, then I would have had x minus alpha on the, I would have had some x minus alpha surviving, right. The quotient, this quotient would have had x minus alpha, right, and then when x went to alpha, that would have gone to 0, right, that would have gone to 0, but we are saying that that is not going to 0, that is actually going to 1 by q. That means a u x must have only one root at alpha, because after I divide it by x minus alpha and I take the limit x goes to alpha, it goes to a constant, it does not go to 0. That means u of x has a simple root at x is equal to alpha, and this allows, since it has a simple root, that means I can use my Newton-Raphson secant algorithms on this equation and recover my original order of convergence, which is for the Newton-Raphson I am going to get quadratic convergence, right. So, if we define a new function u of x, which is f of x by f prime of x, this was my original function, and then if on u of x I do my Newton iteration, if I do my Newton iteration on u of x, I am going to get quadratic convergence, while for f of x I did not have quadratic convergence, right. So, that is a very easy way of converting u f of x to a function such that I have quadratic convergence. Suppose Newton-Raphson is being used, then we can use the usual Newton-Raphson scheme to find the root of u of x is equal to 0. So, this is my usual Newton-Raphson scheme, but now I am using it on u. Then instead of finding the root of f of x is equal to 0, we are using Newton-Raphson to find the roots of u of x is equal to 0. So, now we are assured of quadratic convergence. In addition, we are assured that the root of u of x is also root of f of x, because that we saw by construction, right. So, even though we have multiple roots, we have an easy way of converting it into improving the order of convergence by writing another function which is just the original function divided by its derivative. So, I thought we will cover system of, but we will continue with that in the next class, where we are going to talk about systems of nonlinear equations. Thank you.